World War II, there was a lot of disruption in the area. There were broken records. We also have certain records, like Bangkok has actually been running since 1790. And so we looked at those as well. But we cut these products off at 1940 because the density decreases rapidly beforehand. So all our analysis, at least for now, is 1940 onwards. And if you have any concerns, I'd be happy to address them because obviously the reviewer had concerns as well. So, all right, so here we have, again, I said CRU doesn't have, we don't have a 2016 estimate, but the satellite and the NASA product both show this giant spike. So this is a lot more drastic now when you actually remove, the quote unquote shoddier data from beforehand. If you just look at 1940, this is pretty staggering that it's potentially an emerged temperature. So if we look at the same time series, April's in mainland Southeast Asia, and this is the Niño 3.4 sea surface temperature anomaly plot during December, January, February. What that simply means is a metric of sea surface temperatures in the Central Pacific that we use to measure when El Niños happen, when La Niñas happen. And so if you have temperatures exceeding a particular threshold here, then we call it an El Niño event. If they exceed a certain threshold in the negative anomaly, we call it a La Niña event. So as you can see, this is 97, 98, 82, 83. This is the present El Niño, or the most recent El Niño. And when we sort of crudely looked at it and we actually analyzed it, it became clear that most of these extremes that we did see in the record, they all correspond to El Niño events. So despite the fact that not all Niño events seem to produce extremes, most of the extremes, though, occur during Niño events. So all of the hot Aprils, actually virtually all of them, occur during Niños. And so these extreme April months are all post-Niño Aprils. So this warm tendency of El Niño to shift around whatever teleconnection it does, whatever havoc that it tends to wreak, at least in this region, it seems to sort of push these April months into extreme states, right? But at the same time, you do have El Niño years that don't seem to produce these as well. So we wanted to look at what is the sort of, okay, so we have all this, but here we are connecting some box in the Pacific to some box in, Southeast Asia. What does this look like when we're actually spatially taking a look at this? So what we did, the next plot I'll show you, I'm just averaging temperatures for all the El Niño years, actually all the El Niño years, and I want to look at April temperatures during El Niño years. So when we do that for the two different time series from 1940 to present, CRU tends to go back. We wanted to look at it from 1900 to 2014. This is what it sort of looks like. So this is the average April surface temperature anomaly during all these El Niño events. And what we see is that there is still residual remnant warmth in the Central Pacific after the El Niño, because the El Niño peaks during December, January, February. But there is still some residual warmth there. But what we also notice is that there seems to be exacerbated heat anomalies in this sort of Thailand, Southeast Asia region. So digging into that box that I showed you, we look at the surface temperatures. This is, again, for composite El Niño events. That's the Niño 3.4, where after the peak of the El Niño, it's ramping down. And this is mainland Southeast Asia. The temperature peaks up during April after the El Niño is waning down. And when we looked at the rainfall and cloud coverage in that region, we can see that the rainfall and cloud coverage go down. And we also looked at a surface energy flux budget, and we noticed that the primary driver of this heat increase during El Niño events seemed to be the latent heat due to clouds. So here we are trying to understand the mechanisms for what's going on based on observations, based on a couple of El Niño events that we have. We're trying to see it. Many of these don't come from actual observations. They're from reanalysis data. But we're trying to understand, and what this sort of tells us is that maybe the onset of the monsoon or rainfall that alleviates these extreme heat events, they tend to get delayed. So if the onset of the monsoon is sort of pushed away, you tend to have prolonged heat. And we can see that the clouds basically don't come around. There's lack of rainfall than normal in the El Nino years. And the latent heat of clouds actually, because of a lack of clouds, tends to drive up heat. That's what we're thinking. And so when we wanted to look at some sort of cloud data sets, there's actually fairly decent cloud coverage from the reanalysis, which does a fairly decent job. What we have here is something known as a product called COADS. COADS, which many of you might be familiar with, is actually ship-based measurements of clouds. It's actually quite genius because they're measured in this unit called octa, O-K-T-A. And octa are basically sailors used to look up at the sky, divide the sky into 8 quadrants. And if it's 8 on 8, that means it's really cloudy. Or if it was 2 on 8, 3 on, so they used to estimate it based on, so it's in octa. And so it's remarkable that someone's put together this data set and it actually corresponds. So when we have, again, this is during April and during El Nino events, when we have the remnant warmth in the Central Pacific, we tend to have higher cloud cover, meaning potentially more rainfall as well. And over here, we tend to see an anomalous lack of cloud cover over mainland Southeast Asia. So we're still skirting around to try and figure out. So they show increased temperatures over mainland Southeast Asia, along with sort of decreased cloud cover. But the problem is, in the instrumental record, there's only so many events. So what if it's just 3 giant El Niños producing this pattern? That doesn't really tell us anything about what might happen in the future, or so for now, for the little next part of the talk, I'm going to be delving into climate models and sort of the utility of these models into at least increasing the statistics of trying to understand the mechanisms behind some of these features of the climate system. So as most of you guys know, climate models are basically these giant numerical simulations of the global climate that solve the Navier-Stokes or approximate the Navier-Stokes equation, and you tend to simulate global climate. The one that we used in this study is called the Community Earth System Model from NCAR. And it's fully coupled, meaning the atmosphere talks to the ocean, talks to the ice sheets, and talks to vegetation. Everyone's talking. It's 1 degree by 1 degree resolution, which is not bad considering most models and the current state of the art. And the atmospheric model is known as CAM-5, the Community Atmosphere Model. The ocean is called POP2, is the ocean model. It has 60 vertical levels, 30 vertical levels. We think it's a pretty good model. But we took it one step further because the type of experiment that we used from this model is something known as the large ensemble simulation. This is actually really interesting, at least for me, where what they did, so the climate system is, even though it is a chaotic system, it still depends on initial conditions. So if you rerun a climate model with the exact same initial conditions, you're going to get the exact same output even if you run it for 100 years in the model world. So if you run it for 100 years and have a time step of 5 seconds, you're going to get the exact same thing if you have the exact same initial conditions. So what these guys did, based on work from GFDL, theoretically goes back to Lorentz's work, where he characterized the butterfly effect. And what these guys did is they purposely perturbed this model from 1920 40 different times, but the only difference between each simulation was changing the temperature of a grid box in the Pacific Ocean by 10 to the power minus 14 degrees C. That is the smallest unit that you can change a climate model in. That's the smallest increment that you can do. So they just changed a random box by 10 to the power minus 14, literally a flap of a butterfly wing. And you tend to get just chaos that amplifies, feeds back onto the system, and you get completely different realizations. So it's a very unique experiment. I believe K et al. Came out in 2015 with their results, so it's very new. This data set is completely available for public usage. You can do a lot of cool things in it. It was run with complete chemistry as well. So there's a lot of applications for marine science apart from, say, just climate. But they also had ice, sea ice, a lot of different things, but fully coupled runs. But you have 40 different observations, but they're all forced in the same way because we think we know what CO2 is going to do. So they're all forced with the CO2 business as usual scenario. So what that means is they're all walking differently, but they're being walked towards the same place. So the forced response of these climate models is the same, but the internal variability is different. So the way I like to think about it is between internal and forced, like I showed you at the start. This was an analogy that I got from Michael Tobis, where if you're walking a dog, the leash that you have on the dog, if it's in the climate system, the leash is pretty big. The dog can walk around, right? But you're going from point A to point B. You know exactly where you're going from your house to the park and back. That's what the forcing is. So the dog might walk around, and that's the internal variability. So each one of these, so think about 40 dogs that you're walking, and each one's doing its own thing, but you're going from point A to point B. So the forcing, the carbon dioxide forcing, and all the other forcings that they have in the historical record as well from 1920 to 2010, I believe. So the volcanoes, all the external forcings are the same. It's just the internal variability that's different. So this was specifically designed to try and understand decadal and multi-decadal scale internal climate variability. So some cool things that you can do. This is 1979 to 2012 surface air temperature trends in these models, in each one of these ensemble members. And you can see there's a lot of discrepancies. So for example, some of these models show a cooler Southern Ocean here. Some tend to show cool Asia. Some tend to show warm Asia. Each one does its own thing. Mind you, this is 79 to 2012. So they're walking quite a bit. But when you look at, this is supposed to be 2079 to 2100. When you look at the latter part of the century, when the forcing overcomes most of these internal variability, everything looks very similar. And so it's a nice way. So what you can do is you can basically average the temperature response in each one of these simulations. You take the average, you get one particular giant temperature record. But if you subtract that temperature record from each one of those models, the residual that you're going to get is internal variability in each one. So now you can start to look at, okay, what is El Nino going to do? What are these random climate perturbations that have always existed before anthropogenic forcing? What are they going to do, and how are they going to play out? So again, just to get back to our April composites. So this is again observations, clouds, and this is surface temperature. And when we look at the average of all of these 40 ensemble members from the Community Earth System model, this is what it looks like. So this is from CESM, or what I showed you before. This is from CMIP5, which is another type of experiment where they do different climate models run only once, but the average of that. Whereas this is the same climate model run multiple times, right? Anyway, what does this show? This basically says that Aprils still tend to have the remnant of El Nino warmth. And associated with that, you tend to have anomalously high cloud cover. Both of these sets of experiments show that. But what they also show is a huge anomaly over mainland Southeast Asia. So this is really good. These models seem to reproduce what the observations show. So just to quickly compare, if you want to scrutinize, we have observations, we have simulations. So they tend to do a reasonably good job on what's going on in this sort of region, regional climate signal over here. And when we look at the evolution during in the models, we can actually see that they tend to respond in a very similar way, where after the peak of El Nino, mainland Southeast Asia temperatures shoot up exactly during April. There's a corresponding cloud anomaly covered decrease, and there's a rainfall decrease, and the latent heat of the cloud seems to be what's affecting this region. So it's really good that the CESM-LE captures the link between mainland Southeast Asia and El Nino. And now we're in a really, really good place to try and utilize these 40 different ensemble members, because what they can provide to us is different realities of the planet Earth, which means we can play around with the statistics. We can actually say something about what is happening to these heat events. Can we try and parse them out with global warming versus El Nino? So we're in a really good place because it captures the physics that represent this system. Okay, so I'm going to be showing us a couple of histogram plots. And histogram plots are basically just the frequency of different types of events. In this case, they're going to be April temperature. And in the first two columns are observations. And in this third column is the large ensemble. So of course, because we have multiple more realizations, the y-axis here goes up to 700, whereas in CRU, going for about 100 years, we have around 40, and the real accurate NASA GISS is about 25. And so what I've divided these Aprils into, in the red is going to be post-El Nino Aprils, in the blue is going to be post-La Nina, and the gray is going to be all of the years combined. So instantly we can see in the observations that there's no surprise, but the El Niños tend to be the ones where the extreme Aprils occur. Similarly, the La Niñas are the ones where you tend to have the cooler events. And both of these observational data sets confirm this. And the nice thing is that this is another validation of the model for the exact same region, that the model tends to get this as well, that the El Niños tend to produce the heat extremes and La Niñas tend to produce cooler temperatures. So just, April's after La Nina is cooler, April's after El Nino is warmer. We knew that. Okay, what about global warming? Now in the next plot, what I'm going to show you is, this is for the entire time series, right? What if we divide this time series into two different subsets divided by half? So this would go from 1940 to 1979 or something. This would go till 1950, and then another one go to 50 to 2014. I'm just going to divide the time by 2. Because I want to look at how the long-term trend is affecting these April temperatures. So I have 40 to 77 in the blues. All the former time periods are going to be in the blues, and all the latter time periods in the orange. Again, observations, and we have models. All of them are going to be April temperatures, and this is the frequency. So what we see is that the latter histogram has sort of crept over to the right, aka warmer temperatures for this region. And we see that in the CRU and the GISS temp. These are all statistically significant. And because we have so many observations here, we see the same thing in the ensemble as well. So April temperature extremes have been influenced by long-term warming according to observations and simulations. This is nothing new. If you have a trend from one point to another point and you divide that by 2, you are going to see this. So this is not something that's really unique to this area, because global warming is affecting most places on the planet, but it's a nice confirmation that it is affecting April temperatures. The real question is, how is it affecting post-Nino Aprils? Because these are all Aprils. If you take every April and you put it into a histogram and you impose a trend on it, you're going to see that the histograms get shifted. The real question is, the subset of these that are El Niños, or that are extreme El Niños or post-Nino Aprils, how is that getting affected by global warming? That's what we want to find out. So when we look at that, when we look at the post-Nino Aprils, granted, in the observations, we don't have that many events, but we see that in the observations as well, the Niños from 1940 to 77, the post-Nino Aprils, tended to be cooler than the 78 to 2016 ones. And this is confirmed in GISS temp and in CRU. But this is where the real power of statistics comes in with the large ensemble, is that we have more than 400 or 500 events over here of just post-El Nino temperatures, post-El Nino April temperatures. And even this shows that for this region, these post-Nino Aprils are being exacerbated and being pushed to the right. So multiple lines of evidence telling us that these extreme post-Nino Aprils have also been influenced by long-term warming. So just to summarize our findings so far, climatologically, April is the warmest month. We know this. It's prone to extremes. We know that most of these hot extremes occur during just after the peak of El Nino years. These El Nino events prime mainland Southeast Asia for extreme warmth. And long-term warming in the region appears to worsen the amplitude and frequency of these events. So really, we want to try and figure it out. The nice thing is that there is agreement between the observations and the models. So the last part is to try and think about predictability. We know all this stuff. We've dissected this topic. We've tried to figure it out. Is there any scope for predictability at all? so here's the GISTEMP record, 1940 to present. I want to try and simulate it using a statistical model. So I have surface air temperature based on time, as a function of time. I want to fit a straight line through this with some quadratic component. And what I also know is that this is affected by Niño 3.4, or ENSO. So I'm going to put ENSO temperatures in here, and just a function of time, where t is in years, small t is in years, and capital T is the El Nino departure for that year, the Niño 3.4 departure. So like I said, that's Niño 3.4, that is time. So we just wanted to see what kind of predictability do we have. If we take temperatures in this random box in the Pacific and just take time, no physics at all, this has nothing to do with Southeast Asia, but how well does this predict our April temperatures? Pretty good. Imagine that. We take a box in the Central Pacific and we just put a coefficient there of time, a long-term trend with some quadratic nature to it, and then put in some coefficients, then we can reproduce many of these events really well. That was really surprising to us. So we thought, okay, so we have these long-term warming coefficients, we have the ENSO coefficient. Can we start to think about dividing these up? Because now we have a regression. Can we really look at, okay, how much of this was ENSO and how much of this was long-term warming? What about this? What about this? And so when we come to, say, this last one, the 2016 one, there's also a component where the difference between those, what we label as other, is the unaccounted residual. Yeah?
But if you want to use this for forecasting, you still have to forecast what capital T is going to be.
100%, correct. Right? Yeah, great point. Yeah, if we want to forecast this, we need to know capital T. One thing as a teaser, the T here is the DJF Niño 3.4, whereas what we're forecasting is in April. So it's not going to be seasonally forecasted like well beforehand, but at the same time, it gives us predictability at least 4 months in advance. But I'll come to that. But the other is simply the mismatch between our purely statistical regression and the actual observed April temperatures in this region. So diving into it a little bit more, we can use this as a template for what is known as statistical attribution. We want to know how much of a particular event was caused by global warming and how much of it was natural. This is a classic problem, right? If you have a good, I'm going to use a cricket analogy. If you have a good batsman and someone who's really good takes steroids the day before, if he actually hits 6 sixes or home runs, you don't know which 6 particularly was caused because he took the steroids, or was he a good batsman? So the idea, it's the same idea. If you have extreme events here, is it because this place is already prone to extreme events, or is it because of global warming, the steroids? Okay. So trying to parse that out is important for a multitude of reasons, but it also gets back to this whole emergence concept as well. So this regression, this template right here, can be used